graphing rational functions, so we've simplified them, and that leads us directly into the ability to be able to graph these things. Now, obviously, I know that your calculator will graph whatever you tell it to graph, but there are some specific details that we need to discuss, and that your calculator doesn't just come out and outright tell you about. Just like with quadratics, your calculator won't tell you what the axis of symmetry is. You have to know how to find the vertex of a quadratic. Different things like that we have to worry about with rational functions. They have some special characteristics. From when we were simplifying, the excluded values create holes, what we call holes in vertical asymptotes. So remember I pointed out the two different errors, like one of them was an error and then you got a value, and then the other one stayed an error both times. Well, one of those is a hole, one of those is a vertical asymptote. So if a factor cancels, okay, if a factor cancels, what happens is before it cancels, it causes the function to be 0 over 0, and that creates a hole. Okay, so if a factor cancels, that's a hole. You take that factor that you canceled, set it equal to 0 to find out where it occurs. Okay, so that's scenario number 1. Scenario number 2 is if a factor is left in the denominator. Okay, so after we've simplified, what's left in the denominator causes your function to be undefined. It causes you to divide by 0, and that creates a vertical asymptote. Okay, so those are the two scenarios that we're going to worry about first. If we cancel something, it's a hole. If it's left in the denominator, that's a vertical asymptote. And in both cases, we set those factors equal to 0 to find out where it's happening. Okay? We have another characteristic that we need to talk about, and that is what we call a horizontal asymptote. Okay? Asymptote's kind of a really weird word. You gotta be careful when you're saying it and spelling it. But what it is, it's an imaginary line, okay? Vertical asymptotes, we just talked about those. It's a vertical imaginary line. A horizontal asymptote is a horizontal imaginary line. So it's going to be a dotted line, okay, on the graph. And a horizontal asymptote describes the end behavior. So we've talked about end behavior with our polynomial functions. Where the ends are going. Are they going to positive infinity? Are they going to negative infinity? Where are they going? Well, with horizontal asymptotes, they're not always going off to infinity. Sometimes they're kind of leveling off to another number. So to figure these out, we compare the degree of the numerator to the denominator, and there are 3 scenarios. The degree of the numerator can be greater than the degree of the denominator, and in that case, we have no horizontal asymptote. There's no horizontal asymptote in that case. If they're equal to each other, then our horizontal asymptote is y equals the ratio of the leading coefficients. So say we had 3x cubed as the leading coefficient in the numerator and negative 4x cubed in the denominator. Same degree, so the horizontal asymptote would be y equals negative 3 over 4. And we just take the leading coefficients there. And the third case is if the numerator is less, if the degree of the numerator is less than the degree of the denominator, and that is y equals 0. I'll kind of explain it a little bit more here in a minute when we actually look at an example. And then the last thing we've got to worry about is finding our x-intercepts. And we set the simplified numerator equal to 0, and we solve for x to find our x-intercepts. Okay? So on your worksheet, let's look at number 17. And we're going to start with number 17. We're going to go through the list. Holes, vertical asymptotes, x-intercepts, and horizontal asymptotes, and then we're going to look at the graph. So we need to simplify this as much as we possibly can. The numerator does not factor, so we leave it as x minus 3. The denominator, we can pull out a 4, and that leaves us with x plus 3. Now, sometimes these will simplify, sometimes they will not, okay? They do not have to simplify, so be very, very careful with your signs. Don't mess them up. or you'll end up canceling something that you're not supposed to cancel. So nothing cancels here, so there are no holes, okay, no holes. The vertical asymptote, we take what's left in the denominator and we set it equal to 0 and solve for x. So we've got 4 is equal to 0, which is not true, okay, but I want you to be in the habit of writing it down, because if that was 4x, you would need that, okay, and then x plus 3 is equal to 0, so x equals -3 is the vertical asymptote. So let's graph this as we're finding these characteristics. So at -3, I'm going to come over here on my graph and try to actually hit the line. At -3, we're going to put a vertical dotted line at x equals -3. Okay, that's our vertical asymptote. Label it. Okay, so you know when you're looking back at it what it is. Label it VA for vertical asymptote. Okay, let's find our x-intercepts. Okay, x-intercept, we set the numerator equal to 0. Now, the reason why we do this, let me explain why we're setting the numerator equal to 0. When you are on the x-axis, what is your y value? If you are anywhere on the x-axis, what's the y value? 0, okay? So that means the function is equal to 0. The function is a fraction. The only way a fraction can equal 0 is if the top part of it is 0. So that's why we set the numerator equal to 0 for the x-intercepts. So we get +3 for our x-intercept. Sometimes you have more than one. Okay, sometimes you will have more than one x-intercept. Sometimes you won't have any x-intercepts. Okay, sometimes you will not have any x-intercepts. But you can have 1, 2, any combination there. All right, last thing we've got is the horizontal asymptote. I always go back to the original to figure out the horizontal asymptote. So I look at the original problem. What is the degree of the numerator? 1. Okay, it doesn't have, that x doesn't have an exponent, so it's understood to be 1. What's the degree of the denominator? Degree 1. So they're the same. So we take the ratio of their leading coefficients. So this is y equals 1/4. Y equals 1/4. So hopefully you can be a little bit more detailed than me, but I'm going to try and make this look like it's at y equals 1/4. Okay, so pretty close to the x-axis, but just a little bit above it is our horizontal asymptote. Okay, so then we need to sketch the graph. Well, I don't have a ton of details here, okay, but I can use my calculator to find some more details, right? I can always type in my equation, remembering to put parentheses around it, top and bottom. Let's see if I can go to the table. Anytime I'm graphing, I can always go to the table and see if I can find some nice numbers to graph here. Let's see here. -1, -0.5 is a good point. There's my error at -3 for my vertical asymptote. Let's see here. -5, +1. -5, +1 is a point. They're kind of going down from there, okay? I don't have to pick whole numbers. I just like to graph whole numbers. I could have done -4, +1.75. Put that point in there. Okay, I could have also put in -2, -1.25. You can plot any of these points. But I have a pretty good idea. If I press graph, I need to kind of see what the shape of this is, okay? Here's what a lot of your rational expressions are going to look like. They're typically two separate curves. Okay, now I do realize that looks like it's connected. Okay, it kind of looks like part of a heartbeat monitor. That's what I don't like about these calculators. That vertical line right there that some of your calculators graph is the vertical asymptote. You should not graph it as a vertical line. These pieces do not actually connect to each other. one of the characteristics of a vertical asymptote is that you can't touch it, okay? Because when x equals 3, or excuse me, when x equals -3, we're dividing by 0. You can't divide by 0. That's undefined. So there's no value at -3. That is not a line right there. You cannot touch -3. X can never equal -3. Now, usually you also don't touch a horizontal asymptote, but it is possible to touch a horizontal asymptote. We may get to an example here tomorrow where we do actually cross it kind of in the middle of the graph. But let's look at the end behavior here for a second. On the left side of this graph over here, most of the time when we're talking about end behavior, our y values are either increasing or decreasing. Well, what are they doing right here? They're kind of leveling off. If I look at my table, if I go back to the table for a second, as I go further and further to the left, look at what these y values are doing. They're getting smaller and smaller and smaller, and if I go far enough, they're getting really close. See how these are all like 0.28? What was my horizontal asymptote? 1/4. That's 0.25. I could also do it if I went way far off to the right. Let me show you something. If you need to skip to a value on the table, press second window, and you can tell it to start at 100, okay? And I'm going to go back to the table, and it jumps me to 100. Look at these y values, okay? They're 0.23. We are just below our horizontal asymptote way over here on the side. Okay, so horizontal asymptote is describing where your function is headed on the extreme ends. Okay, so we'll pick up with this tomorrow. We'll do some more